Because of the intimate connection between our definite integral and our antiderivative that the fundamental theorem of calculus gives us, I need a better notation. I really don't like the idea of just writing this capital letter to indicate the antiderivative. That's dumb. What is the antiderivative of 1 over x? The natural log of the absolute value of x. But wait, there's more. Thank you. I don't know if I told the story here. My high school calculus class, my negative score, don't forget the plus C. I earned negative points on that homework assignment. Don't forget the plus C. Okay. I want a better notation than just this capital F. And since we're using these to do integrals, the only thing I'm not doing is plugging in the numbers. So let's take our definite integral symbol, that elongated S, and strip the numbers off of it. This is called an indefinite integral. And this represents our antiderivative. So in general, when I write the integral of f of x dx with no numbers on it, what I'm looking for is that function f of x, where capital F prime is little f of x. I'm looking for my general antiderivative. But rather than just think of it as a general antiderivative, I'm going to call it an integral. But that means we know now how to write these things more compactly. By writing these as integrals, I'm really asking you, hey, find a bunch of antiderivatives for me. We did this. What's the integral of x squared? That's the derivative. I got to go the other way. This is going to be a very common occurrence. I'll say, what's the integral? Somebody will give me the derivative. That happens all the time. I have to remember I'm going the other way. And I can't forget my plus c. The antiderivative, the integral of e to the x, is e to the x. I got to go to my pattern matching idea. I don't know how to do quotients, but I do remember on my formula sheet, 1 over 1 plus x squared shows up, and that goes with my inverse tangent. Now, because inverse tangents give me angles, you might also see this written as the arc tangent, since an angle in radians is a measure of arc. It doesn't matter what letter we're doing. Remember, the letter is irrelevant. If I write it in t and I'm integrating dt, it means I want to think of this as now my variable is t. What's something whose derivative is secant squared? I'm done. I just have to remember it's in t, not x. Page 410. I would like to point out to you that you really only have to have in your head 4 of these. I'm sorry, 6 at most. What do I do with a constant? pull it out front. Same rule for derivatives. What do I do when I'm adding? Oh, I just separate them, add. Integral of a constant gets an x. Power rule. E to the x, ln of x. That one's on the formula sheet. So are all of these, with the exception of the last two, because we didn't do those at all. They're not going to be on anything we do. Those are hyperbolic functions. If you're interested, they're back in chapter 3, section 11, but you can write them in terms of e, so we don't normally bother with them this way. So I really only have to know 1, 2, 3, 4, 5, 6. The rest of them are on my formula sheet. But that means I need to know what's on that formula sheet so I can recognize it and go, oh, wait, that's something trig. That's something inverse trig. That's the logarithm with the weird base. I'll go back to the formula sheet for it. So something like this applies all of those ideas together. I want the antiderivative of 10x to the fourth. What do I get? X to, that should be a 2 up there. That's a really bad looking 2. That's so x to the fifth over 5. I multiply by 10. That gives me a 2. X to the fifth. We just did secant squared. I changed the letter. Oh, big deal. The negative 2 stays there. Integral of secant squared is tangent of x. Oh, yeah. Don't forget my plus c. I'm anal retentive about that because I really don't want to leave off the parentheses on the argument of my trig function. I promise that will make more sense on Monday. You'll see it in the book without the parentheses. That's fine. If you write secant squared x and then you write tangent x, I'm not going to throw a fit. But I promise there's a reason I put parentheses around these. Oh, here? That's also an option. Well, but what else would be? The whole thing is inside the integral, isn't it? All of this dx. Because that's what we did up here. We just wrote f of x dx. Yes, there may or may not be parentheses around this entire thing. Depends on the setup. More questions? We may need to do some algebra to get things to look like we can understand what's going on. No. I know, but you've got a glass forehead. I can read what you're thinking. I don't know how to do quotients. I certainly don't know how to do quotients with trig functions in them. There is no inverse quotient rule idea where I could undo my quotient rule that way. But I can play with what I know about trig functions. We've got a sine squared on the bottom. So let's separate that into two pieces. Cosine over sine, what function does that give me? It is cotangent. One over sine. Cosecant. Trig functions are on formula sheets. Go get the formula sheet. It's on the back of the exam, or it's on the exam review sheet on our Canvas page. If you took it off your exam, there's a copy available for you. It's available for download on our Canvas page. What's the formula? What's the formula involving cotangent and cosecant? Wrong folder. It's in this one. What's the problem? There's a negative sign there. I don't have a negative sign. Well, I would like to add one in, but I remember that if I add something in, I change the problem, right? What's the only thing I'm allowed to multiply by? It doesn't change stuff. We did that in the limits, right? So I'm going to multiply by 1. But I'm going to multiply by 1 by multiplying by -1 twice. So there are my two -1s. Now, the very first rule on that table on page 410 said if I had a constant inside my integral, I could take it out front. So I'm going to take this minus sign out front and leave this one inside. And now that matches my formula. So I do my antiderivative and I get cosecant of theta with the minus sign left on the outside. Adjusting for numbers like this to make things look like the way I want them to is going to come in handy. Yes, ma'am. Because the only thing I'm allowed to multiply by is -1. No, the only thing I'm allowed to multiply by is 1. -1 times -1 is +1. So it's like I put one inside and one outside so they would cancel out each other. So I just put them both on the inside to start with. More questions? Fundamental theorem of calculus says that the definite integral is the antiderivative evaluated at both ends. So really, when I do this, what I'm really doing is I'm saying, oh, I want you to do this, and then I want you to plug in the A and the B and subtract. So a definite integral contains in it, hey, do an indefinite integral first. So the first thing I need to do is the indefinite integral. I need to do the antiderivative. Antiderivative of 2x cubed. All right, ignore the 2. What's the antiderivative of x cubed? So the 2 stays out front, 1/4 x to the 4th. The antiderivative of x. Almost, Avery. Say again. Now I'm working with the x. I go to the x squared, what do I do with the 2? Divide by it. So the 6 stays there, and I get 1/2 x squared. Ignore the 3. 1 over x squared plus 1. The inverse. When we looked at it on the formula sheet, it was 1 over 1 plus x squared. I don't care what order you add in. That's the same. So the 3 stays there, and I get the inverse tangent of x. I'm doing a definite integral. What can I do about that plus c? I can ignore it. Because I'm going to plug it in, and then I'm going to plug it in again, and I'm going to subtract. The c is going to cancel no matter what I do. When I'm doing a definite integral, I can leave it off. Well, now I can plug stuff in. I think it might be better to simplify these two first. But now, plug in and give me some numbers. Three to the fourth is 81. 3 squared is 9 times another 3 gives me 27. Tangent inverse of 3, I don't know that off the top of my head. I'll leave it like this. And then I put in 0. 0 to any power is 0. 0 to any power is 0. Tangent inverse of 0. That one I do know. What's tangent inverse of 0? 0. The problem with tangent inverse of 3 is it's disgusting. 81 over 4 minus 27 plus 3. Tangent inverse of 3. Oh, you're right. It's over 2, not over 4. Tangent inverse of 3 is not a nice number. I'm not going to get a useful number in terms of pi or anything like that. So just give me a decimal. We're good enough. 17 point, however many decimal places, the number of significant figures in your problem calls for. Again, why is having a decimal good? I can make the graph and check it. A common mistake. I'm evaluating the antiderivative at 0, right? Here, I plugged in 0, the whole thing was 0. But here, what's e to the 0? I cannot tell you the number of papers where people have written e to the 0 is 0. Oh, I'm plugging in 0. That whole thing must be 0. No. I'm going to leave that like that. I don't even know what the number is. I don't know how to deal with quotients. Well, now it's not a quotient anymore. Okay. Distribute that because I still don't know how to deal with products, but I can multiply through. And that I can do. What is the antiderivative of y to the minus 2? And multiply by 1 over the new power. New power is -1. 1 over -1 is just a -1. Antiderivative of 5y to the 4th is y to the 5th. Evaluate from 1 to 2. Oof. I started to write 32 and I started to write the parentheses at the same time. So I wrote my 2 really small, like an exponent. That's not good. 32 minus 1 over any number is 1. Sorry, 1 under any number. That works. 1 to the 5th, 1. Oh, that's zeroed out. Hey, look at that. I didn't even plug in 0, but the second set of parentheses turned out to be 0 this time. Questions? Yes, ma'am.
But for like the first part of them, like whenever it doesn't tell us to give like X amount of decimal, should we leave it as the exact or round?
As long as you're rounding to a couple of decimal places, 2, 3, something, I'm fine with that. If you got an exact answer, like, I don't know, square root of 2, leave it as square root of 2. If you got an answer where you end up with trig functions, you know you're going to get stuff in terms of pi, leave it like that. Like our e problem up here, I left in terms of e. I could give you a decimal. I'd rather see that for me. But if you want to be able to check it, you're going to need to know the decimal. So that's going to depend on what you want to do with your answer once you've got it. I jumped past this problem, but something like this requires me to rattle off values out of my unit circles, so I should know those. Trig functions. Secant tangent is the derivative of secant, so the antiderivative is secant of theta. Now, I'm the absolute first person to tell you I don't have the values of secant of theta memorized. That's bullshit. My unit circle gives me sine and cosine. Secant is 1 over cosine. So that's really all I need. But now I need the value of cosine of pi over 3. Say again? Right. So that's 1 over a half, which gives me a 2. And then cosine of pi over 4. Say again? Or square root of 2 over 2, depending on which way you want to write it. Yeah. But if it's square root of 2 over 2, when I flip it, it'll become 2 over root 2. If I write it as 1 over root 2, when I flip it, it'll become root 2. But I'm just going to leave that one and not bother to do any sort of decimal approximation. That's an exact answer. I'm perfectly happy with that. Make sense, Jonathan? More questions? No, I can actually try and describe what happens as my upper limit goes off to infinity. But that's well past where we're going to go this semester. Oh no, but it is applicable. Chapter 7, section 7. I've got the question none of you asked me yet. Why? Why am I doing this? Torture? Well, yes, but if these weren't useful, you'll pardon the pun, this would be nothing more than mental masturbation. No. No, there needs to be a use going on here. What is this good for? If I think of an integral, and I think about what happens in my fundamental theorem of calculus, this is a change. It's what changed in capital F between point A and point B. But the change in capital F, change in means derivative, right? That's little f. So I'm accumulating all of these little changes together. If I'm adding up a bunch of change, that's net change. So I can really think of a definite integral as a summation, as an accumulation. Let's consider a function little v of t, which represents the amount of water entering or leaving a reservoir. I'm measuring change, right? How many cubic feet of water came in or how many cubic feet of water left at different points throughout the day. So at time 0, midnight, I look at the amount of water coming in or going out. I'm pretty sure few people are doing their laundry and taking showers and all at midnight. I could be mistaken. It's college campus, y'all are night owls, sometimes. I would wager that there's going to be a lot of water use between 5:30 and 8:30. The kitchen turns on and people start doing dishes and cooking, and everybody gets up, takes a shower, flushes the toilet, all of this wonderful stuff happens. And then the water level builds back up over the course of the day. And then lunchtime hits, kitchen goes off again. Evening time hits. There are some pretty clear things I can do here. Did you know the City of London tracks this information during Wimbledon? The US tracks it during the Super Bowl. Because I kid you not, the power of the synchronized toilet flushes almost blew out the London sewer in the Wimbledon finals. And the same thing happened at not one, not two, but over half a dozen different football stadiums during the Super Bowl. At halftime, the pipes nearly burst. How much water did we use in the day? I got to pay for water. My water bill comes every month. How much water did I use? I can add up all of the water from time 0 to time 24 and tell you how much I used. Maybe more water came in than was going out, but I don't know. But I can certainly measure that. Consider a rod made up of a material whose density changes. Somebody, chemists, units for density. Grams per. It could be liter, it could be cubic centimeter, it could be milliliter, whatever, but it's grams per volume. Right? So let's say I don't know, how long is this particular piece of material? Let's say it's, I don't know, 2 meters. And I could measure the density from one end to the other. I'm also going to make the assumption that the rod is uniform in thickness. So it's the diameter or the width, depending on the shape, is the same all the way down. I'm a crappy illustrator, but we'll run with it. How much does it weigh? I have no idea, but I know how to measure it. If this is the density in grams per cubic per cubic centimeter, then I could say, oh, let's slice this up and measure the weight of each slice. Well, the weight of each slice is the density times the volume of that slice, but that's going to depend on how thick it is. And if I let my thickness get smaller and smaller and smaller, I can think of measuring this by adding up little tiny slices. My density times a volume in cubic centimeters, right? The volume of a slice. That's mass. I said the material was the same size from end to end. I didn't say it was the same density from end to end. This is an empty glass cylinder with a piece of sublimating iodine at one end. There'll be iodine gas slowly spreading throughout the whole thing, right? But the concentration of iodine will be really, really high at one end and really, really thin at the other. Density changes as I go along. Because I said it was 2 meters, and this is per cubic centimeter, so I need to do it in centimeters, don't I? Back to the units issue with kilometers per hour and seconds from the homework. Hey, wait a second. We talked about marginal revenue, right? What was marginal revenue? What did that mean as an idea? But marginal cost and marginal revenue and marginal profit. What was our marginal revenue meaning? This is back in chapter 3, applications to business and social sciences, chapter 3, section 7, I think. It's the amount of money I bring in if I make just one more. Change in revenue per change in number of units, dRdx. What if I don't raise my production by 1? What if I raise it by 30 or 40? What if I go from a production level of 200 units to 280 units per week? How much does my revenue go up? Well, it goes up by the integral of the marginal revenue. So a change on margin tells me a net change in revenue. Production. I got excited. My writing gets sloppier. Remember our ball being thrown off a cliff? If I have a velocity equation, v of t, a velocity function, and I integrate it, what does that represent? Oh, acceleration is change in velocity. That's derivative. It's position. Aha. Change in position. Net change. Just like it was the net change in revenue, this will now be net change in the thing that this is the change of. The net change in position. And since this is a function of time, v of t, it'd be between time A and time B. So here's the velocity equation. I'm back in feet again. Yep. What's my net change in position between time 0 and time 4? The antiderivative of 32t, well, t becomes t squared over 2, so I get 16 t squared with minus sign on it. 64 has no t's, so it gets t. Plug them in. What? How is this a 0? I hit a home run. I started home plate. I ended home plate. My net change in position is 0. Crap. That's all this measures is endpoint minus start point. And it turns out the height at exactly the same time is the same. I started and ended at exactly the same height. All right, wait a minute. I'm going back to my physics class. There's a word for that. What am I measuring when I only measure change in position by taking final minus starting? Displacement, not distance traveled. So if I really want to account for the fact that I was moving in the middle there, I somehow need to turn all of my velocities into positive numbers. So I measure the amount I went in one direction, the distance, and then I turned around and came back, I need to change that from being the opposite direction. I need to make it positive. I need an absolute value. Okay. Because I don't know that it automatically was half. If I knew I spent just as much time going in one direction as going in the other, then I could be sure that what I want to do is cut this in half. I don't know that automatically. It is true in this case, but this case is rare. So how do I fix this to get it to be correct if I didn't know that it should work out to be right in the middle? Because I went up, I stopped, I came back down, I had to turn around halfway through. If I'd started on top of that cliff, right, I would have gone up for a little while and then down for a lot longer. So I really need to be careful. What's the graph of that? Y'all took out your calculators to plug in the numbers. Draw me the picture. What kind of graph do you get from this expression? It's a linear equation. I get a straight line. It starts up here at a height of 64, and it finishes down here. Because the slope is the negative number. This is the part that's the problem, this part that's underneath. I do. And I do that by setting the velocity equal to 0 there. And I get t equals 2. An absolute value takes a negative number and makes it positive. That's the same as multiplying by -1, right? So up here, I'm going to use this equation. But down here, I don't want to use the same equation. I want to multiply it by -1. So instead of doing this as one integral from 0 to 4, I'm going to break it up in the middle. This is one of those properties I talked about yesterday. I'm going to split this into 2 pieces. I'm going to go from 0 to 2. And then I'm going to go from 2 to 4. But the absolute value changes in the middle there. Here, we use this equation. But here, we multiply by -1. And each of those integrals, when done separately, give me the distance I went going up, and the other one gives me the distance I went coming down. And since I started and ended in the same place, those do turn out to be equal this time. I rigged the problem. My application depends on my setting. But the idea of what accumulated, I don't know, like something precipitating out of solution over time? Filters? I don't know, you pouring coffee? You know, a pour over, the water has to percolate through all that stuff. How long is it going to take? Useless. Never going to use it anywhere. Everywhere. I need to figure out better ways of doing antiderivatives, and then I need more applications. I will see you all on Monday. Have a wonderful weekend.